Hi everyone, welcome to our video. I'm Kaining Zhang from the University of Sydney, and I would like to present our work towards the trainability of quantum neural networks. In short, this work provides lower bounds on the gradient norm for quantum neural networks with certain structures to show the absence of Baron-Plateau's problem. The full version is available on the AQIS website. Firstly, the motivation of this work is to avoid the Baron-Plateau's problem during the training, which exists in random quantum neural networks. In short, the Baron-Plateau's problem means the trace value of quantum observables in the parameterized quantum circuit concentrates around its acceptation value, with a variance epsilon that could be very small compared to the system size. We provide a detailed description of the Baron-Plateau's phenomenon in this slide. Consider the objective function f for the n-qubit quantum neural networks defined as a half plus a half times the trace of observable O for the quantum circuit B theta on the input state rho in. Then, the partial derivative of f to any parameter theta g has the acceptation value 0, and the acceptation of the square of this partial derivative is bounded by epsilon. For quantum neural networks with random structures, epsilon could decay to 0 with the order exponential to the qubit number n. Such a small gradient norm could lead the following issues that then influence the trainability. Firstly, exponentially large number of measurements is required for relatively accurate gradient estimation. Secondly, the objective function itself tends to have a flat landscape, which is naturally hard to train or to provide useful information. To address this problem, we explore the architecture of quantum neural networks with a target to prove a larger lower bound on the gradient norm. Our contributions are summarized in several following slides. Firstly, we prove lower bounds on the gradient norm for two kinds of quantum neural network with special structures, namely the tree tensor structure, which we refer to as the TT, and the step control structure, which we refer to as the SC. These two structures are illustrated in two figures on this slide. In short, the tree tensor structure comes from the binary tree. The step control structure consists two parts. In the first part, CNOT operations are employed between adjacent channels, followed with single qubit operations. In the second part, CNOT operations are employed between different channels and the first channel, followed with single qubit operations. We denote NC as the number of CNOT operations that directly link to the first channel in the step control circuit. We remark that every single parameterized gate in the circuit here is the sigma y mutation gate. About the bounds of gradient norm, we prove that for the tree tensor circuit, the gradient norm is larger than inverse of 2n times a constant alpha rho in, and for the step control circuit, the gradient norm larger than inverse of 2 power nc times a constant alpha rho in. Alpha rho in here is a constant depends on the input state rho in that defines as the sum of trace for certain observables to the input state. The acceptation is taken for all parameters in theta with uniform distributions from 0 to 2 times pi, and the quantum observable in the circuit is chosen to be the sigma z on the first channel times the identity on the rest channels. The second part of our contributions is that we prove by employing the L-layer alternating circuit for encoding the input state, the acceptation of the value alpha rho in could be further lower bounded as the inverse of 2 power 2L. The encoding circuit are illustrated in this slide. Similar to the quantum neural network, such an encoding circuit is constructed through training parameters. More details are provided in our paper. Okay, The last part of our contribution is that we simulate tree tensor circuits, step control circuits, along with random circuits on the binary classification task. Both tree tensor and step control circuits show better trainability and accuracy than that of random circuits. The detail of employing quantum circuits for the binary classification is shown in the algorithm 2 here. We define the loss for a training batch as the average of the L2 distance between the label and the objective function. Parameters are updated through stochastic gradient descent. In this slide, we provide more details about the test accuracy and the FE score of the classification task for different classification class pairs in the MNIST handwritten number dataset. For all experimental settings, tree tensor circuits and step control circuits show higher accuracy and F1 score than that of random circuits. We also provide the definition of accuracy and the F1 score here for convenience. In this slide, we provide more details about the classification task for different QB numbers. Tree tensor circuits are denoted in red lines, step control circuits are denoted in brown lines, and random circuits are denoted in blue lines. For QB number 8 and 10, both tree tensor and step control circuits show accuracy higher than 0.8, while random circuits show some sort of trainability with accuracy between 0.7 to 0.8. For QB number 12, the tree tensor and step control circuits remains good trainability, while the random circuit has the accuracy 0.5, which is no better than a random guess. We also count the gradient norm in the bottom left figure, which shows larger gradient norm for the tree tensor and step control circuits compared to that of random circuits. The value of alpha rho in for the training data are shown in the bottom right figure, which shows bounded average value. In conclusion, all theorems are verified. Further directions of this work are summarized as follows. Firstly, we could extend assumptions on quantum circuits in this work to the single qubit rotations that not limit to the sigma y gate, and to explore other structures or other quantum observables. Secondly, some high-level analysis could be derived with form that not only rely on certain structures. Lastly, we could further analyze the difference between this framework and the two design frameworks. Since the gate operation here shows less randomness than that of unitary 2 designs, we wish to obtain some stronger lower bounds. That's all. Thanks for watching our video.